In this lesson we're going to look at how the reaction rate is affected by the surface area of the reactants, again in the context of collision theory. So just to start off with, let's imagine we've got two substances reacting. The blue particles represents one substance and this sort of grey matter here represents the other substance. And as we mentioned in the previous lessons, it is not possible for any reaction to take place unless there is a collision. That is what collision theory is all about. So for the blue to react with the grey, the blue particles must collide with the grey lump. And in fact, if you look closely at this diagram here at the moment, you'll only see that I think 3 particles are on an online collision course. It would be that one too. That one may hit, it may miss, whatever. But the point of this is that if we want to improve the chance of a collision in this situation, what we need to do is to reduce this grey substance here into smaller particles. Okay, so let's do that. Yes, spread them around evenly. Okay, what we've done then is we've improved the chance of a collision. So in fact, if we look now, then that one's online for a collision. This one will be. This one will be. This one will be. This one, just about. That one. I think we'll give that one the go-ahead. And that one, I think the only one in this diagram which isn't, is this particle. So we've greatly improved the chances of a collision by reducing the grain size. In fact, what we do when we reduce the grain size of the reactants is we increase the overall surface area of the reactant, and it is that which increases the frequency of collisions and increases the chance of a successful reaction. Let's just make a note of that. So by introducing a smaller particle size or grain size, we're going to increase the overall surface area of the reactants. And I'll have a look at that in a minute just to convince you that that is actually what happens. And by increasing the surface area, then we're going to have a greater number of collisions, and a greater number of collisions means there's a greater chance of a successful reaction. So I just would like to point that out here because it is important that simply guaranteeing that there's a collision or improving the chance of a collision does not guarantee that a reaction will take place. Remember, in the previous lesson, the reacting particles have got to have enough kinetic energy to ensure that the activation energy is reached and that the reaction can take place. The kinetic energy on impact is only really influenced by the temperature of the reactants. It is not influenced by the surface area of the reactants, but the surface area is very important in increasing the reaction rate because it does increase the probability of a collision between the reactants and therefore the number of collisions that are actually taking place. Now, I'd just like to convince you about this whole business about reducing the grain size increases the overall surface area. So let's just have a quick mathematical analysis of this. So imagine here I've got a cubic grain, 3 centimeters by 3 centimeters by 3 centimeters, and what I'm going to do is I'm going to cut it into 3 equal sections along the 3 axes of the grain. So for example, we'll cut down this way. Okay, so first of all, let's quickly calculate the surface area of this cube. Well, as you know, it's 3 times 3 is 9 and 6 faces, so 6 times 9 centimeters squared gives you 54 centimeters squared. Alright, that's the overall surface area, and as a result of cutting it this way, I'm going to get 27 equal cubes of 1 cubic centimeter, and the surface area of this cube will be 6 centimeters squared. So I've got 27 6 centimeter squared cubes, which gives me a total of 162 square centimeters of area. I've got 27 of these. So clearly by reducing the grain size, I've increased the overall surface area. And the smaller the cube size that I produce, the greater will be the overall surface area. Okay, so surface area, very important in increasing reaction rate. Let's just have a look at a practical demonstration of this. Again, we're going to stick with our hydrochloric acid and zinc, for example. So we've got equal amount of equal concentration diluted hydrochloric acid, and this time we're at the same temperature. We're going to keep the temperature constant, keep it at 20 degrees Celsius, and we've got equal volumes. We want to keep everything constant. The only thing we're going to change now is we're going to have the same mass of zinc. There we go, we've got a lump of zinc in this flask. I'm going to use the same mass of zinc in the other flask, but it's going to have a much smaller grain size. Okay, so in one case we're using a lump of zinc, in the other case we're using powdered zinc, for example, and but it's the same mass. And again, you remember from the previous lesson that the reaction between zinc and hydrochloric acid, as you well know, gives you aqueous zinc chloride plus hydrogen gas liberated. Let's just balance that. And as you can see in this apparatus, what we're going to notice is that there's going to be a difference in the rate at which the hydrogen is liberated in the two flasks because of the difference in surface area. And you'll see straight away that in this flask the piston of the syringe is pushed out a lot faster, okay, because hydrogen is liberated at a faster rate because the reaction goes at a faster rate because the grain size is smaller, and therefore the overall surface area is larger. So we can say smaller grain size, larger surface area, higher reaction rate. Therefore this piston moves faster. Okay, in the next lesson we'll have a look at how the concentration of the reactants will affect the reaction rate in a particular reaction.